I'm going to be talking today about ghc-exactprint, which is a piece of joint work between myself and Alan Zimmerman. It really all started a few years ago. Alan Zimmerman had taken over the maintainership of Hair, which is probably the most well-known refactoring tool for Haskell. But it wasn't going too well for him. He was finding it difficult to update between GHC versions, and he was finding that was because the foundation just wasn't really strong enough. The foundation used to be based on a token stream approach, which he found to be quite brittle with the changes we made to the GHC AST. So we went back to the drawing boards, and he went back to the drawing boards and came up with this new idea for a refactoring foundation, which did require quite a bit of work with GHC. But now we've finished the implementation really, and we're hoping that tool writers can get using it to rewrite the refactoring tools that Haskell has promised for many years. I'm going to talk about the problem, the solution, and a few applications, and a bit of future work if we have time. So if there's anything people want to hear more about, just let me know as we're going through, because I'm not really sure which parts are interesting to the general audience. I mean, I've spent a lot of time inside the implementation, so that part is quite fresh in my mind, but to the general audience, it might not be your cup of tea. So let me know if you want to skip further on to the applications or something like that. OK, so it's probably good to start with a demo of what is now possible with this tool. So my Google Summer Code project this summer was to use the tool to apply H-lint suggestions automatically. So most people are probably familiar with H-lint. It's a tool which gives you useful suggestions about how to refactor your program so it's more idiomatic or sometimes more correct or just things like that. So I was writing this source file this morning, but as you can see, there are a few errors which have popped up. Like I accidentally imported the same module twice, and that's probably undesirable. So I'm going to press my key binding, and then the import disappears. That's it. So we'll go further down the file and just there's a redundant parenthesis. We'll get rid of that. Good job. This rather silly expression, we can apply a few refactorings to that, and just keep going down, keep applying the suggestions until we reach the true definition of RDO. This one is a bit more interesting. We have a call of unsafe perform IO here, which we should probably add a no inline pragma to, so this doesn't get evaluated multiple times. It's executing our IO action multiple times. So H-lint has a suggestion, which is to add a no inline pragma, which we can also insert. Add some extra spacing there. Here, there's another H-lint suggestion, and we can also remove the redundant do. And finally, we have something a bit more complicated. To have this expression here, this declaration here, which is can be written in terms of a fold. H-lint recognizes this, and then we can apply it. This here is equivalent to sum. We apply it once again, and we end up with a nicely refactored source file. So this kind of thing wasn't really possible before, because I mean, it's obviously possible to find these hints, as H-lint has done for quite a number of years. But the real difficulty before was rewriting these hints back to the file, like the really boring part. Like all the interesting intellectual part was already done. So myself and Alan have been left with the task of working out how to come up with a format which makes it also easy to rewrite the files so the program can automatically apply the hints. Simon. It's quite a basic example of refactoring because H-lint only operates using the GHC parser. So none of these hints required renaming or type checking, so it's all quite basic, and written with the low-level API which we provide now. But more complicated things are possible. But that's the idea of what is now possible. Yes, question?
So the demo which you just did was not just H-lint, it was with these new tools as well?
Yes, so how it works is I've added changes to H-lint. H-lint calls this new executable which I've provided, because the tool I've written uses the GHC API, right? And it's not really desirable to depend on GHC. So we've got this bit of a weird architecture going on where H-lint calls this external tool which then performs the hints.
Thank you.
OK. Right, so what was wrong with the old representation? Are people here familiar with Haskell SourceX? People used it before? OK, a few people. So Haskell SourceX provides its own parser for Haskell and its own syntax tree. And people tend to quite like using this because it's quite a convenient representation. So the first thing we wanted was a more natural API for refactoring. But the second thing is we wanted to use a GHC API because we wanted to be also get hold of the rename source and type check source for more complicated things, such as renaming or lifting to the top level and making sure we don't have name clashes. So these are the two things that we wanted to do. And there wasn't really anything which hit the sweet spot between the two. I mean, Haskell SourceX is convenient, like I said, but perhaps isn't powerful, and it's doesn't, for really serious applications, it isn't sufficient. So we wanted to choose a representation which was good for refactoring operations, but the most important refactoring operation, as far as I'm concerned, is the identity refactoring, right? So the identity refactoring is doing nothing at all. And as you can guess by the name ghc-exactprint, like, we spent a lot of time just applying the identity refactoring to files over and over and over again to make sure if we didn't change anything, then the source files didn't change. Because that's quite an important thing. If you change something at the top of the file, you don't want to then change the bottom of the file to change unexpectedly. So we spent a lot of time doing that. And this is really important to remember as we come up with more complex representations, because it is quite easy to implement just on its own. But we also want to have more things like adding parameters, moving expressions, and so on, which require something slightly different. So people expect refactoring tools to be quite easy to write, and they expect, in this case we're doing some simple inlining, they want to be able to pick up the case expression and just move it to where the subdef is without really changing anything. They want to be able to write a generic function which does that. But it turns out this isn't really possible, because there's quite a few things that you need to think about which aren't in the ghc-ast. One thing, for example, is that previously the location of keywords isn't recorded, and also you have to think about. Yes, I'll get to that in a minute. So in a traditional compiler, all source locations are absolute. So in order to describe maybe where this expression is defined, we might say it's on the 4th line in the first column, for example. And that's really great for most compilers, because it's useful for programmers for error messages and things like that. But for our purposes, it's not so great. For example, if we want to do this inlining transformation, we can't just move the case expression and do the inlining, because if we do that, all the source positions will then just be completely out of sync with each other. If we just move the case expression and don't change any of the source locations, it will no longer be on line 6, line 5. It will be on line 3, and that would be completely wrong. So how do we then print it out? So our solution to this problem, which is the key idea of the library, is that we turn all these absolute source positions into relative source positions. So that's to mean, instead of describing that the case is on line 5, we actually describe it as it's one column further on than the equal sign. We describe where the expression is. We describe, oh, that is 2 lines further on than the module header, and so on and so on. So by describing it like this, we can move expressions around wherever we like, and all the positions still make sense. Wherever we move that case expression to, the true branch will still be 1 line further on than the false branch. So we can move things around much more easily and don't have to worry about all these things like updating source positions. So that's the key idea. Right, so the question is, where do we store this information about these relative positions? And the obvious answer would be, you store them in the syntax tree. You just replace all the source locations with all the new relative positions. But for the ghc-ast, everything's already baked in, so you can't do that. So we have this it works, but we use the original source locations as indexes into a map, which then tell us how far, tell us all the relative positions. Yeah, I can see your faces in the front here. I mean, this is not nice, but it does work, and I mean, it makes our lives easier in some ways. More difficult in others, I understand, but yeah. These are the main data types we use. The main one to be of interest is the annotation data type. So this describes this is how we describe the location of the keywords and things like that. So the anentry delta, that's how far it is from the previous element, whether it's a comment or a keyword or anything like that. Then we have a few things for comments which we have to deal with separately. And then ansdp, which is not a great name, to be honest, describes the location of keywords inside a syntax element. So I think I have an example. If people want to ask me about these last two, then they can, but I mean, it ruins the niceness in some ways. Right, so once we have this, like I said, we can move things around freely most of the time, and we don't usually have to worry about the annotations. The time when we worry about the annotations is when we move something maybe to the top level, then we want to say, oh, it's 2 lines further on. But a really important thing is that if we move an element, we don't have to then look inside and change all the annotations inside. We just change the annotations to the top level case expression or whatever we're dealing with. So, do you have any questions at this point? Okay. Right, so when we generate this map, there's a bit more we have to do. We also have to know which keywords can occur with which syntax elements. The way that we do this is we basically write down which ones can be associated with each syntax element, which is also quite a tedious task. We build up a free monads which has some information. So for example here, we have a type family instance declaration, and we mark down, okay, it has the type keyword, it has the instance keywords, there's the equation, and then it might have a trailing semicolon. We're doing this for every single syntax element. The reason why we use a free monad rather than just a list or something a bit simpler is that it really is quite convenient to have this flexibility when you're iterating quite quickly, I think. Like, sometimes we do use the power of the monads, even though we really shouldn't. We do have quite a lot of constructors for this approach. We probably don't need all of them, and I wish we didn't. But we still need to. We want to reduce the number of constructors if we can, because inside things do get a bit messy sometimes. Okay. Right. The first step, once we have this free monad, is we take the syntax tree and make all these relative positions using the information we have in the structure. That's one interpreter we have. And the second interpreter is the printing. One way we can print it is just back to a string, so it looks exactly the same as before. But it's actually possible to generalize it a bit further. So we provide functions which describe how to surround one of the elements. We have a function which describes how to surround a token, and a function which describes how to surround the white space. And using this, we can actually get some nice syntax highlighting, which I've not seen done anywhere else in Haskell. So, for example, if I hover over these declarations here, and they turn bold, the whole declaration turns bold. So people don't seem very impressed by this, but I was quite impressed with myself when this happened, because more complicated things are possible. So, for example, oh, that's quite small, isn't it? Can people see that? Nope. Can I make this bigger? Can I make this bigger, anyone? Command plus. Oh yeah, there we go. Okay, can people see that? Right, so the idea is here, this is a mock-up I made of a possible web interface for HLint. So you paste your source file, and you press the button, and then it highlights the expressions which need refactoring. So you can give it more complicated information. I think there are lots of other things you could do with this, but these are basic things. Okay. Right. So a lot of the time with this library was actually spent testing it, and we now know it does work really well. We do have a library that can do absolutely nothing, which is a great feeling. We ran it on every source file in Hackage, all 65,000 of them, and we only had at the end 40 failures, which I think is a fair success rate for this sort of thing. There's a few well-defined things which don't work, like minimal definitions in type classes. If you use them, probably don't use this. If you have multi-line strings in pragmas, probably don't use this, as it will probably not work too well. But only 40 files out of 65,000, I think, is a fair return for this sort of thing. But this did come at a cost. We did uncover many parser bugs in GHC doing this work, because I don't think people have really debugged the source locations before on syntax elements. It's not a very rewarding task. But now now we've done so hopefully no one ever has to do it again. Right. So what does it? Okay. So now I've painted a very rosy picture of what works. I'm going to put my hand up now and say not everything does work. Okay. The number one thing which doesn't work. Can anyone guess what it is? I've told some people already. Yeah, that's right. I heard it. The CPU processor is evil. It really, really makes things very difficult for us. I mean, we can handle quite standard if-defs and things like that, but if you have more complicated CPU processing stuff, then things fall apart quite quickly because we have to run the CPU processor, find out where the differences were, convert the different parts into comments so we can reinsert them afterwards. And if you have inline macros like ghc does, for example, we really can't do a great job. So I plead with you today, please use the compact modules if possible. I know there's been quite a lot of mailing list discussion recently about the CPU processor and using compact modules. I don't wish to get involved hugely, but from my perspective, the compact modules seem to be a good thing for avoiding the CPU processor. Another issue as well with the CPU processor is that you need the Cabal macros file in order to properly resolve it. And that requires quite a lot more infrastructure to try and find it. And if it's not been generated already, you need to run Cabal build in order to generate it. And this ruins the locality of the approach. You can't just take a single source file to understand what it means. You have to take the whole project to understand what it means, which makes our job also a bit harder. It's the same with extensions as well, which you can listen to the Cabal file, and if you just take a single source file, you can't tell that whether this source file needs certain extensions to run. Certain tools like HLint get around this by just turning on all extensions, but I don't know. That seems to work quite well, but we didn't want to do that. Right. Also, there's the Haskell is quite quite expressive. Let's just say. I think this one's from 1993. This source file, so Leonard might recognize it. It's part of the obfuscated Haskell competition. And in fact, this isn't one of the more difficult source files for us to deal with. It's actually quite standard vanilla Haskell. And even though we did catch some bugs with source files like this, which was quite satisfying, and now these do work as well. We can refactor files like this if we want. But what's more difficult is just weird extensions that no one uses. So who has used the transform list comp extension? Yes. We have a winner. We have two winners. Oh, this is excellent. It's only used in, I say 5 packages. It's actually used in 5 source files in the whole of package. But it probably causes more grief than 95% of everything else. It's just retrofitted. Some of these extensions are retrofitted retrofitted into existing syntax, and things are rearranged in the parser. And at the end of the day, you fix the bug and you feel really great, and then you realize only 5 files use this. So that's taken us a lot of time to get through all of them. But all extensions will now work, apart from the CPU processor. Right, now this is probably the interesting part of the talk. Like, what can we do with this? So there's already a few applications which we've been working on. The first one I've already shown you, which is called Apply Refact, which uses HLint, which hopefully will be released soon. But the main consumer is Hair. So I don't know if people saw, but we just recently released the 0.8 release of Hair, which works with ghc 7.10.2, finally. And that currently supports a few things. We have converting if expressions to case expressions. Yes?
What is Hair?
Hair is the Haskell refactorer. We have renaming, and we have demotion, promotion, duplication. So I've talked to a few people. One person asked me if it supported renaming. Yes. Another person asked me if it supported promotion and demotion. The answer is yes. So I think we can say we support 100% of refactoring operations desired by the Haskell community. So that's it. Thank you. No. Anyway, so I have some demos of hair in action. Here we go. I didn't record these. This one here, we're lifting a definition to the top level. This is very nice Emacs integration. You can see the diff of what happens, and then on the right you can see that it has been lifted to the top level. Do we want to perform the change? Yes. And on the left, it's now been lifted to the top level. So that is now possible. Ooh, I have some very interesting suggested videos here. OK, we shan't watch any of these, but we shall watch another video. Here we go. Here's number 2. This is an example of renaming. We should work cross-module, I've been told, if you cross your fingers. So this one here, we're going to rename the x's to something else. Again, very nice Emacs integration. And did that work? I hope so. Yeah, I mean, did that work? Yeah? Yeah, OK, good. So hair works using is name aware as well. So renaming should work properly. But even though we just released a new version, we only support 6 operations. And in 2001, there was this paper released called A Catalogue of Functional Refactorings. And that included 21 refactorings. So we're only a fraction of what was, we're only a fraction of the way there in what was specified in 2001, which is quite a long time ago now. And there's also this quote from Simon Thompson, which I think sums up our feelings quite well. You get quite a long way the way there, but there are lots of things which you have to do to make a refactoring tool work, like deal with cabal, deal with dependencies, deal with the CPU processor, as I've already been on about, to a boring length. And yeah, so this is something that I think people should be aware of and just reflect on in their own time. Yeah, so here's an example of hair working 6 years ago with a really old version of GHC, and you'll be able to see in a minute that there's many operations which we don't yet support, and it has Vim integration for starts. I don't think we have Vim integration yet, so we're still working on that, trying to get back to where we were. But the hope is that we have a much firmer foundation than was previously there. Right, so that's what Alan and I have been up to. A project which is was not me or Alan, was by Andrew ghc-exactprint. I don't know if people have heard the proposed argument do extension. It passed around on the mailing list a bit, but Andrew wrote a project called ghc-reskin, and the idea of this project was that he wrote his own. He modified the GHC parser a little bit, then he wrote a preprocessor which used his modified version of the Haskell parser to parse the source files he wanted to parse. I have an example on the next slide. So this is the example. So below is the example of something he wanted to parse. The top is a valid Haskell program today. So he wanted to get rid of the $, really. And so he used his modified version of the GHC parser. Then he used ghc-exactprint to print out a valid Haskell source file, which allowed him to, because it was a preprocessor, it allowed him to write programs like this if he wanted. People could then try out the extension because it was only changing the syntax in a slight way, which I thought this was quite a novel use, which I hadn't previously thought of the library. So I was very pleased for him to pick it up and try it out. I think that's a good use. Another thing which people may be aware of is the monad fail proposal and the monad no return proposal. Again, people have probably seen it on the mailing lists. Although I'm just going to talk about the actual refactoring rather than what I think of the issue. So the thing about these proposals is they're actually very well defined. People try and define them extremely well, so no one's surprised when the change happens. I think that ghc-exactprint could be used to perform these refactorings automatically. Maybe not just running it on all package. Library authors should probably observe the changes before they publish them. But it should be quite easy to perform a refactoring such as this. So here we have a monad instance which has the fail method. The monad fail proposal is in essence removing the fail method from monad. So and introducing a new class, monad fail, which has the fail method. It slightly changes the desugaring as well for denotation. So the refactoring operation is simply we take the fail method from this monad instance, and we'd rewrite it, introduce a new instance of monad fail, copying the definition. So I think Alan and I are going to try and write something like this so people can at least try it for their own programs, and we'll see how well it works. But I'm quite hopeful that it'll be useful to at least get 95% of the way there. Yes?
That would be even more useful if it inserted CPP.
Right, so yes, it was. This has been mentioned, and there's no technical reason why we could not insert CPP as well. But could I sleep at night if I inserted CPP? I don't know. So we'll see how strongly the public demand it.
We settled for you staying awake.
Right, so, okay. Any questions now before I get on to something which is maybe tangentially related, but is not part of the main ghc-exactprint yet. It's more of an idea in my head. So do you have any questions now? Simon?
So one of the things you haven't made a lot of stress on, which I think has worked out rather well, is this idea that for the locations of the keywords, instead
Yes, so I thought about this a bit, and the real problem is deciding where you reassociate comments with. So we have quite a naive rule at the moment where we associate the comment with the immediately following syntax element, whatever that is. So sometimes that doesn't work too well if we have a comment at the end of a line, because it will be associated with the next declaration. I think there'll be a similar problem for haddock comments and deciding where they should be located. But I think it's probably a bit better defined where you can associate haddock comments. Yeah, so it might work a bit better.
it's fully defined, right? So
Right.
decluttering the tree would be great.
Yeah, I think it would.
It might simplify habit too.
I have tried implementing more complicated general comment balancing stuff, but it never really works properly. But for haddock, I think it might be okay. Any questions? Yes, Ollie?
Is ghc-exactprint doing any kind of symbol?
Somewhere in HLint it says that fold R plus is yes, but the HLint has quite a powerful custom rules. You can specify your own custom rules. So if you have a specific function you want to rewrite, then this will also work with any custom rules that you define. Because the way it works is quite, especially for replacing things, is really quite general. Any more questions, or should I just go and talk about pattern synonyms for a few minutes? Okay. Then, okay. Okay. So I've talked a bit so far about how we can provide a nice API for refactoring, but people like using HaskellX. I don't know whether it's because it's not GHC or whether it's actually nicer to work with their syntax representation, but there are quite a few libraries which do use it. So maybe more of a personal curiosity is I was wondering whether it would be possible to provide a library which looks like HaskellX, but is based on GHC's API. So we can use GHC's parser, not have to keep updating two parsers, and I think it probably is in GHC8 after I finish implementing the right features. So has anyone here used pattern synonyms before? Who's familiar? Okay, we have quite a few people who are familiar, but I'll just explain for people who aren't. So in my head, pattern synonyms is not really a great name for the feature, especially for bidirectional pattern synonyms. It's much better to think about pattern synonyms as if they are defining data constructors separately from the types which they construct. So, for example, here is a pattern synonym. It's called myJust, and there's a simple definition here. myJustA equals justA. And once we've defined that, we can use it for one of two things. We can use it in a pattern context to pattern match as if it is a constructor. We can also use it in an expression context to build a maybe. So pattern synonyms are really about more than just giving new names to patterns, which I think is a bit confusing sometimes. What's really great is that, in theory, they allow it to change the implementation whilst keeping the interface the same. Previously, if you exported the constructors from your library and you changed the internal implementation, then really you were going to break all your users' code. But now you can, by defining a set of pattern synonyms on top, you can keep the set of pattern synonyms the same, change the internal representation however you like, and nothing should break for users. Right. So I just want to talk about two things that are wrong with pattern synonyms currently and will hopefully be fixed for GHC8. So, right, just to be clear, the goal before is, if we have a program which uses Haskell source X, this may be a typical import. What I really want to be able to do is just provide a new module and just change the import line to the name of my new module, and for everything still to compile properly, but to use GHC underneath rather than Haskell source X. I don't know if it's possible yet. I've not actually tried to implement it, but I'm hoping it is. This is already used in a few packages like PSQs, which has 3 different implementation of a priority queue, and you can just change the import to decide which implementation you want to use. So, right. So like I said, pattern synonyms are, it's good to think of pattern synonyms like data constructors. I had some conversation with Simon today where he was telling me maybe they're not exactly like them, but it's good to think about them as if they are. But there is a problem that you have to explicitly import and export pattern synonyms. So in that way, they are not like data constructors. With data constructors, you associate them usually with the type which they construct. This is the syntax for importing and exporting a simple pattern synonym, whereas it would be much better if you could associate this pattern synonym with the type it constructs. So when the user imports the type, then they are not aware whether they're importing data constructors or pattern synonyms. That is something that you can't currently do, but should be in GHC8. Is that clear to everyone? Okay. The next thing is record pattern synonyms. So there's 3 types of data constructors you can either define: a prefix, infix, or record data constructor. Currently, you can only define prefix and infix pattern synonyms. So there's a clear hole where you can't define record pattern synonyms. That is, a pattern synonym which looks like a data structure, but is not associated with any type. So for example, this declaration here, which I've implemented in GHC, would define this pattern synonym myPoint. And myPoint, this pattern synonym myPoint should behave very much like this data constructor myPoint here. So when we define it like this, we define 2 fields, x and y, which are both of type int. But instead of building a point that's defined here, we're building a point as defined here. So this sort of syntax will define selectors. It will allow record updates with points, even though there are no record constructors defined for it usually. And myPoint should behave like a record data constructor, but it is not. So these are the 2 things that might make pattern synonyms closer and closer to actual data constructors. So library authors can provide a set of pattern synonyms for whatever interface they like and really hide the internal implementation. Okay, that's it. Any more questions? Yes? So it might be better if the library author requests for their code to be refactored, rather than if I just start submitting hundreds of pull requests with ordering everyone's import lists. It might not go down too well. Next question? So implementing cosmetic changes is a bit more difficult because then you need to go into the annotations and you need to go into the annotations and things get a bit more fiddly. But that's definitely possible. We want to maybe try writing a pretty printer inside the library, which would create annotations and insert keywords rather than just taking the output from GHC. So if you gave it as a part of the AST, then it would create annotations for you, maybe some sort of configuration, try and pretty print it. But that's something else that we might have to work on. Yeah.